Hello everybody, welcome back to OR1. On this video, we will discuss the transportation model and its variants. So the content of this video coming from the textbook, especially from textbook number 3, Taha 2007, Operations Research and Introduction, A edition. So the transportation model and its variants consist of three models. Number one, the transportation model itself, the transshipment model, and the assignment model. In this lecture, we will only learn two of them, which are the transportation model and the assignment model. We will not learn the transshipment model. The transportation model and its variants, they are the special cases in the linear programming. Basically, they are linear programming model that we can solve using simplex method. But we will not solve them by using the regular simplex method. We will apply a special algorithm which is designed to solve the transportation model and its variants. The algorithms, they are based on the simplex algorithm too, but they are more efficient comparing to the regular simplex algorithm. So I repeat, the transportation model and its variants, they are the special cases of linear programming problem. We can solve them by using simplex method, but we will not apply the simplex method directly to solve the problem. We will apply special algorithms which are designed to solve them, and those special algorithms, they are more efficient comparing to the regular simplex method. We will start from the first model, which is the transportation model. Example 1, it gives you the description what the transportation model is about. So the transportation model, it is about sending some product from sources to destinations, which the sources, they have limited capacity, and the destination, they have demands. Okay, let's see example number 1. So M6 Auto has 3 plants in LA, Detroit, and New Orleans, and 2 major distribution centers in Denver and Miami. The capacities of the 3 plants during the next quarter are 1,000, 1,500, and 1,200 cars. The demands quarterly at the 2 distribution centers are 2,300 and 1,400 cars. So the mileage between the plants and the distribution centers is given in table 1. Okay, so from table 1 we know that the distance between LA and Denver, they are 1,000 miles, and we also know the distance between the other plants and the distribution centers. And the trucking company is charged of transporting the cars 8 cents per mile per car. Give the LP model of this problem. So the linear programming model of the problem showing in example number 1, that is a transportation model. Okay, so it is very clear in this problem that our objective will be minimizing the total transportation costs, and our decision variables will be the number of cars that we will send from each plans to each distribution center. Given that we have to satisfy, number one, the capacities of each plans and the demand from each distribution center. So we have three constraints on this problem. Constraint number one is the capacities of the plan. Constraint number two is the demand from the distribution centers. And constraint number three is the number of cars that we have to send. They cannot be a negative number. They can only be a positive number or zero, and they must be an integer. So, however, before we develop the model, see that we have the cost data. They are the cost data is in cents per mile per car, but our decision variable is in cars. So we have the distance data right here. So we need to make the cost data in cents or in US dollar per car, because our decision variable is in car. So in order to make the cost in US dollar per car, so we need to multiply the cost in cents per mile per car with the distance in mile. So that is what we gonna do now. So we have our plans in LA, Detroit, and New Orleans. And I'm gonna label them as LA as the plan number one. So it is so we have three row for LA, row for Detroit, and a row for New Orleans. So LA we're gonna be so I'm gonna label a row as I, so I equal 1. So this is I equal 1. This is Detroit 2 and New Orleans as 3. Okay. And we have two distribution centers, so they are column. So we're gonna have J equal 1 and we have J equal 2. J equal 1 is the let's see, Denver and Miami. Okay, so this is distribution center, distribution center. Okay. So in the transportation model, the I, or in this example, they are the plans. In general, we call it as the sources. So they are the sources. Okay. So the distribution centers, or the column, in this case, we call it as the destination. Okay. So the source is basically from where the product's coming from. The destination, it is basically to where you transport the product. Okay. So from the source, because the source is the origin of the product, we have the total supply. So this is the total supply. And from the destination, they have demand. So we have the total demand from the destination. Okay. Now, from the data, we know that the capacity of the plant in LA, it is 1,000. So it is the total capacity of the the source number 1 or the plant in LA, which is 1000, and then the capacity for the source number 2 is 1500, and for source number 3 is 1200, and the total demand is 2300 for destination number 1, which is the distribution centers in Denver, and 1400 for the distribution center in Miami. Okay, so the decision variable will be the number of cars that we will send from each source to each destination. So let's label that as X. So we're gonna have X11. Okay, this is X12, so X13 and X23. So what is X11? X11 is the number of cars that we will send from source number 1 to destination number 1. So in our case, the source number 1 is plants in LA, and destination number 1 is the distribution center in Denver. So in general, our decision variable gonna be Xij. So Xij, where Xij is the number of car we send from plant I to distribution center J. So that's the meaning of the decision variable Xij. Okay, so here we have I equal 1, 2, and 3, and we have J equal 1 and 2. Now, before we start writing the model, we need to do a little calculation for the cost data. As I explained previously, we need to make the cost data in US dollar per car, because our decision variable, the Xij, is the number of cars. So I'm just gonna copy this table. Okay. Okay. So we have the distance data. This is 1000. Okay. It is 2690, and 1250, 1350, 1275, 850. Sorry, so here we have also the decision variable. I forget to write them down. So this is X23 and X33. Okay. So this is the distance data. So this is distance. Okay. Now, so we know that the cost of sending the car is 8 cents per mile per car. So we're gonna make them in US dollar. So 1 US dollar is 100 cents. So it is 8 over 100 US dollar per mile per car. So we need to make the cost in US dollar per car. So we need to multiply the cost in US dollar per mile per car with the distance. Okay. So this is the cost of sending from LA to Denver. So it's gonna be 0.08 times the distance. Okay. Okay, so those are the costs of sending a car from each source to each destination. So I'm just gonna make them, uh, I'm gonna round them into no decimal place. Okay. Okay, now I think we are ready to model the problem into a linear programming model. Okay, but before I start modeling, again, we need to check, is the total demand equal the total supply, or we can say that is the problem balance. So let's see the total demand. So the total demand is 3700, and the total supply is, it is also 3700. So the transportation algorithm, we can only run the algorithm when the total demand equal the total supply. When the total demand does not equal the total supply, then we need to make them equal by adding dummy supply or dummy demand. We will learn that in the next video. Now let's model the problem. So I think I need this data. Okay, and I also need this data. Okay, now we agree that our objective function will be minimizing total cost. So it will be minimize z equal, so that will be 80 x11 plus 215 x12 and plus till the end 68 x33. So that's the objective function. Now our first constraint, it is the capacity of the plan. So the total capacity of plan number 1, it is just 1000. So x11 plus x12 cannot be more than 1000. So x11 plus x12 must be less than or equal 1000. So the number of cars that we send from the source cannot be more than the capacity of the source. So x13 plus x23 must be less than or equal 1500, and x23 plus x33 must be less than or equal to 1200. Number 2, it will be the demand from the destination. So the total number of car received by destination number 1 is x11, x12, sorry, this should be x12, and I have a mistake of it. This should be x31. Okay, so I'm gonna so x2 x11 x12, so x21, so this is x22, so this is x31, and this is x32, sorry. So I'm gonna, okay, so I'm gonna delete this table. I'm gonna copy this table. Sorry for that mistake. So x11 plus x12, so this is, so now it is a mistake again. We have a mistake again. Okay, sorry. So for the Detroit, so it's be x21 plus x22 less than or equal 1500. And then for the New Orleans, x31 plus x32 less than or equal 1200. Okay. So again, there is a mistake over here. This should be 68x32. Okay. Now the next constraint will be the demand from the distribution center. So the total number of cars received by destination number 1 is x11 plus x21 plus x31. So x11 plus x21 plus x31 must be equal 2300, and then x12 plus x22 plus x32 must be equal 1400. And the last constraint, which is the non-negative constraint, so xij, okay, must be positive and integer, where I, we have 3i, 1, 2, and 3, and we have 2j, and j equal 1 and 2. Okay, so this is the LP model of the problem presenting in example 1. So this is an example of the transportation problem. It is very clear that the LP model here, we can solve them by using a simplex method, but we will not do that. We will apply a special algorithm to solve the mathematical formulation. So in order to apply the spatial algorithm, we need to implement this model into a table. So remember, we have 3 rows and 2 columns, so we need to make a table consisting of 3 rows and 2 columns. So we need to make 3 rows and 2 columns. So I'm gonna make it bigger a little bit. Okay. 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 So now we have the table, which is 3 rows and 2 columns. So we have row 1, row 2, and row number 3. And we have column number 1 and column number 2. So the row will be the destination. Oh, no, sorry. The row will be the source, and the column will be the destination. So from the row, we will have total supply. So we will have supply. From the column, we will have demand. Okay. So for example number 1, the supply from source number 1 is 1000. From source number 2, the supply we have 1500, and source number 3 it is 1200. The demand, this is 2300, and for destination number 2 it is 1400. Okay. Now we also need to put the cost data on the table. So we put the cost data on the top right corner of each box. So the cost of sending the car from source 1 to destination 1 is $80. So we put it here. Okay. So this is $80. So that's the cost. And here the cost is 215. And the cost here we have 100. 108, 102, and 68. And in the cell, we will put the decision variable. So this will be x11, x12, x21, x22, x31, and x32. And we will find the value of x11, x12, and x32 until x32 by using that spatial algorithm. And by doing that, by using that spatial algorithm, we can also identify which variables are the basics variable and which variables are the non-basic variables. And we will use this table to run that algorithm. I think that is it. We will explain the algorithm in the next video. Thank you very much.